Hello. Hi guys, good morning. Welcome back. And in this frequency problem of weekly contest number 380, problem number 3. It is the most hardest problem. Problem 4 was a much more easier because it is based on a standard KMP or Rabin cap, depending upon what you want to apply. You can apply any of these, but this is the hardest one. Again, in this I'll teach you a trick which you should remember for bit manipulation problems. It's the best trick which you can actually used to figure out the number of bits in a range of integers. That's gonna be helpful for you guys. I'll recommend watch this video entirely, and I'll give the intuition of every step of the proof. I'll also give the proof of the trick also. Cool. Let's start off. It says that we are given an integer k and an integer x. First, the problem itself might be a bit confusing to understand, so let's understand that itself. Now it says that consider S is the one index binary representation. So usually you have a zero index binary representation, right? Which means that if I represent a number, let's say 5, so I can represent that as a 1 0 1, and I say this is the 0th bit, this is the first bit, this is the second bit. Now he is saying that instead of saying it is the 0th bit, first bit, second bit, you will say it is the first bit, it is the second bit, it is the third bit. So this is for number 5 binary representation. It is a number 5, right? So I'm representing that as a S, which is consider S, and now it is saying it in a form of a one index binary representation. Cool. Okay, great. Of an integer nums, which means this is a num, which is 5. I represent that in a form of a binary, which is called as a S, and that is I represented that. Now the price of a number num is the number of i's such that I is modulo by, like, I mod x is equal to 0 and S of I is a set bit, which means that if I want to find the price of this specific number num, then it is nothing but the number of such i's, which means you have these i's 1 2 3 4 and 5 and so on and so forth, right? These are the i's. Now I have to find such I, which means I mod x, which means this is the I for me. I mod x, now x is given to me, I mod x should actually be a 0, which means I should be a multiple of x, which means if my x is a 2, so I can only take a 2, I can only take a 4 and so on and so forth. If my x is actually a 3, I can take my x, I can take my I as a 3, a 6 and so on and so forth. And along with that, it says that S of I should be a set bit, which means if I take that, okay, that's great, I'll take that, but that bit also should be set, which means this should be a 1 right here. If I take a bit 6, which means I can take I as 6, so for sure this bit should be set. The bit should be set here, value should be have been a 1. That is what it is saying. Then I can take the price of it. Now for it, the price will be number of such i's. You will see that how many out of all these i's from 1 2 3 4 5 up till like, let's say what is the number, we'll see what is the number, it is 52 53, but up till that number I'll go and iterate all of my i's, and first condition is that I mod x should be actually equal to 0 and corresponding that bit should also be set. Then I'll say, okay, all such number of i's will actually contribute in the price of that specific nums. So in this case, if my x is actually a 3, I will go and try for 3 6 9 and so on and so forth, but you will see that 6 9 all of them will actually having a bit as 0, while only my third bit is actually saying, again, third bit is by representation of S. Actually in our terms it is the second bit by the standard binary representation form. So by this form it says that, okay, this bit, third bit, is actually a 1. So I'll say, okay, my price will be a 1 because I could only find one I. I could only find one such I which was satisfying both of these conditions. So price will be actually a 1 for this. Okay, great. Now comes return the greatest integer num. Again, we are saying for one of the nums, we saw this operation for one of the nums, we have to return the greatest integer nums such that the sum of prices of all numbers from 1 to num, which means I'll try for 1 2 3 4 up till num. I'll try for that num value up till, I'll try for all these values, I'll get the prices of all these values, I'll get the price, let's say p1 p2 p3 and so on and so forth up till p num. I'll get the prices of this, all these values, p num, and the prices, the sum of, which means p summation of from 1 to num. This prices sum should be less than or equal to, my k, which means this prices sum should be less than or equal to k. What is that maximum num I have to find? This is the question itself. Now let's understand that how we can solve it. So firstly, one very basic brute force approach which will come to your mind is, bhaiya, okay, you are saying to find the maximum num, na? You are saying to find the maximum num. Maximum num you are asking me to find, na? That is what you are asking me. So what I will do is, I will start off and say, okay, my num, let's say I'll start off with one number, okay, one number. Then I'll start and say, let's take two numbers, let's take three numbers, let's take four numbers, let's take five numbers, let's take six numbers. I just keep on increasing my numbers, and corresponding, again, when I'm increasing my numbers, corresponding to every of those numbers, I will have to find the power value, right? Because, okay, this is the num. My problem was saying 1 up till the num value, you have to go and try, and I know that it is the summation. So for sure, my summation will keep on increasing. If I add some value, if I add a number, let's say next time I add a number called as 7. So for sure, my sum will increase, because adding something will actually always increase the sum. So I for sure know I will keep on increasing my sum. That is one thing. I know this is linearly increasing. That is one thing. Okay. Now I also know that, okay, for a number, let's say 4, I need to find out its power. I need to find out, because I need to sum up. I need to sum up the powers and not the numbers. So I will have to figure out the power of all of these numbers. That is one operation I have to find, which means I'll go on to all of my numbers. Let's say my number is number which I have to find out. I'll go on to all of my numbers, and I will keep on computing the powers of those numbers, of every number. Let's say I went on to a number 7. So I'll just simply compute the power of this number 7, which means I have to compute the power of 1, 2, 3, 4, 5, 6, 7, and then I'll add them up. If I add them up, okay, 1, 2, 3, 4, 5, 6, 7, I compute the power, and power. I'll add them up, and then I'll check if it is less than equal to my k. Then it's great. I'll try for the next value. But if it becomes greater than k, then I'll say, okay, last one, which means last of my nums was my answer. Now, this is the approach which we can for sure take. That's a very obvious approach, but can we try? So if we go on and say, okay, my value can start from 1, and it go up till where? How far it can go? Okay, now num I can keep on going. So right now I have no idea, because it is the k. K is the sum of powers. K is my sum of powers of my nums, from sum of powers. K is my sum of powers from 1 to nums. This is my k right now. So one thing is for sure, that right now I might not know exact number of where the nums can go, but roughly I can say it might touch my k. Again, there's no exact number in my mind. I cannot, and I don't even have enough time to derive that, but I have a rough idea that, because I am doing a power sum, and there's also a mod operation, which means it is not that, okay, my sum will keep on increasing exponentially or something like that, because I have some restrictions with me. Which means I mod x should actually be 0, the bit should be set. So these are some restrictions which will actually bind my power value. So for sure, the sum value will also not increase that much as it goes on further. So for sure, my nums might touch my k. So that is one thing. Again, I might not know, but my k value is very high. It is only 15. 115. So no matter what, I can't even try for 1e5 or I can't even try for 1e8 values, which means num value as 1e8, which means it goes to 1e8 times. That also I cannot even try. So that is one thing. And neither I have not much time to derive that what will be the power values and the summation values. That is also, which is I cannot spend my time on, because intuition says that okay, it can be a big value because it can be something. Now k is 8, that is okay, obvious that okay, k is 8, which is decent. Maybe I can use this in my future algorithm. Now coming on back, now I got to know that for sure I cannot linearly try for my nums value increasing, right? So I need to do one thing. I got to know while I was deriving this, I got to know that for sure I am next, because I am just increasing my nums, which means I am adding a new value, which means right now here I added a 7, here it was 6. So for sure I'm adding some value. So for sure it will be increasing, which means I know it is for sure increasing. If something is for sure increasing, then I would know one thing. I want to find some value, because you say okay, it will be for sure increasing, which means okay, right now my sum is less than equal to k, less than, now it will be not equal to, like it will be more than k. So for sure you saw something, okay, right, wrong. In this kind of thing, which we can apply simply a binary search. So one thing I got to know, I can simply apply my binary search on this range of nums. Again, nums can be worst case at max k, which we found, but yeah, we already figured out that it will be, nums will be less than k something, but worst to worst case it can be k, right? So what I'll do, I'll apply binary search on this nums value. Now for safety nums value, for safety I'll keep it as a k limit, which means I'll try my nums starting from 1 up till less than equal to k. That is a binary search range for my nums. Okay, I know that this is my range for binary search, I'll apply. But in general, you know that okay, in binary search you reach on to a mid. Now you are at this mid. Now saying okay, now it is saying that your nums is actually a 6. Because binary search will say okay, right now okay, you will try for this nums range, for sure I'll do a mid like L plus R by 2, so I'll reach to a num like value. Now this will indicate me, bro, you have to go and find from 1 up till the nums, you will have to go and find the corresponding power values, which means p1, p2 up till p nums, and then sum them up and check if it is less than equal to k. Then you can try for L is equals to mid plus 1. Let's say your mid was actually your nums, which is on which you are doing a binary search, right? So you will try for L equals to mid plus 1, and else you will just say okay, if it is more than k, then I'll just say R equals to mid minus 1. That is how my binary search applies. But do you see one issue in this? Now for this, when okay, I reduced my answer by using a binary search, and I said that okay, I just do a binary search on my nums, and I know my nums limit is actually from 1 to k. That's for sure. And also when I am at a particular state of mid, I will have to find the power sum, for which I will have to iterate on from 1 to nums. Now I already saw that okay, my nums can be up till k, which means this value can be in worst case up till k, which means, or maybe even k by 2, that's also fine, but it can be, and k was 1e15, so even 1e9 I cannot iterate from 1 to 1e9 numbers. So this is again an issue. Just to find okay, at a mid value to find the power sum, I will have to iterate from 1 to 1e9 or maybe more value, which means 1 to nums, and nums is bounded by k. So I am saying okay, I will have to iterate from 1 to k to actually get the power sum. That is an issue. So although I reduced my time complexity, earlier I was trying for k values, okay, I reduced to log k by saying okay, my nums range, I'll do a binary search on it, but as soon as I'll do a mid, I will have to iterate on from my 1 to nums, which is actually also bounded by k. So this will not work again. Even after using a binary search, it will not work. Now we have to apply some other trick, which means I cannot use this. So I will have to find a shortcut that okay, if I ask you, bro, I will give you a number. Let's say I'll give you, bro, I'll give you a number. Let's say I'll give you 100. So you, bro, have to figure out you bro have to figure out the number of set bits from 1 to 100. Again, you bro have to figure out the number of set bits from 1 to 100, which can actually help me get the answer. So now my main task is to figure out the number of the set bits. Now bhaiya, the condition on set bits were that, okay, x mod I should actually be equal to 0. Sorry, I mod x should actually be equal to 0, and bit should be set, and bit should be set. Let's say bit is set at ith index, yeah. So I'm just saying the same thing. This condition I will firstly try to satisfy, which means I will try to satisfy and bring out the number of set bits in this range. Okay, from 1 to 100, how many number of set bits are there? But bhaiya, how will you use this condition? So what I'll do is, that, okay, I know that from 1 to 100. So I know that I can represent my number I can represent any number in my binary form, right? So I just have to figure out the actual values, the actual like bit sum, right? So I just say that my power is nothing but for a number 1. For number 1, he will contribute 1. Right now, let's forget this. Let's only keep, okay, what is the set bit corresponding to every number. So for number 1, he will contribute 1 at the 0th index. 0, 1, 2, 3, 4, 5. Again, we are back to our indexing as 0, which is the normal indexing basis. Now, as the number 2 will come in, he will have a 1 contribution in the first bit. As a number 3 will come in, he will have 1 contribution here. So this will become 2 and this will become 2, because he will have a contribution, because you know that 3 is actually a 1 1. So this is how, and let's say a 4 comes in, so here he will have contribution here. Let's say a 5 comes in, he will have a contribution at this location, which is at the bit as 2, and here also. So I will again with this, okay, now up till here, up till number 5, I have made a kind of my bit sum array. It is showing me that, okay, up till number 5 corresponding to every bit, this is the bit sum, which represents, okay, these are the number of set bits at this location up till so far. So again, that is what I wanted. Again, power is what I wanted, and this is corresponding to every of these bits. But power was having one more condition, that I mod x should actually be equal to 0. So if I'm saying my x is equal to 3, so I will only include this bit. I'll ignore this bit. I'll ignore this bit sum. I'll include this bit sum only, because ultimately with the problem logic, this was actually a 1, this was a 2, this was a 3, this was a 4, this was a 5, this was a 6. So I'll include this bit sum in my sum value. Let's say my sum value is answer. So I'll include this number 2. Then I'll go on to next number, which is 6. I'll include its whatsoever bit sum value I have computed up till so far. I'll add that in my answer. And this value should be less than equal to my k. Now, this is the high level overview which we have to achieve. So ultimate aim, coming back to ultimate aim. Again, I'm not saying it's an easy problem. It's actually hard, and that's it. That's how you actually understand this. Coming back to our basic logic, what we just wanted to have from 1 up till some value of num. We want to know all the set bit, all the number of set bit at all the corresponding locations, which means at 1. Which means at the 0th index, what is the location at the first, at the second, and the third. I just wanted all the number of set bits up till some specific point, and that's how what we're gonna see a trick right now, how to solve it. So for your understanding, to make you understand the trick itself, I have represented all the numbers in a binary form. Right now, start off. Let's say if I ask you your n, the number is 13, which means your num number is 13. So your num is 13. Now num I represented by my n. I'm saying my n is 13. Now my ultimate aim, अपना मकसद नहीं भूलना है, goal नहीं भूलना है. What was our aim was for a up till number 13, 0, 1, 2, 3, 4. Up till number 13, I have to get this array filled. Now what is this array representing? This is a bit sum array representing, okay, from number 1 to number 13. I'll go on to every number, okay, I'll go on to 1 2 3 4 up till number 13. I'll go on to every number, and correspond to every number what all bits have, what all set bits are there, I will keep on adding those in my this bit sum array. For 1, as I showed you, I'll add a 1. For 2, I'll add a 1. For 3, I'll add a 1 here, so it will become a 2 2. For 4, I'll add a 1 here. For 5, I'll add a 1 here, and I'll add a 1 here. So this is how I have to bring out my bit sum array. So again, we will see a trick to fill this array. How? So firstly, if I have a number 13, which is my last number, which is my nums, which is I have represented by n. So first, foremost basic thing is, okay, you have this as a bit. So one thing is for sure, if I have to compute my bit sum array, everything after it, again, it is make sure it is a 0 based. In the end, we will, by doing a I mod x thing, we will make sure that we are handling this one case, which the problem was saying. But right now, to understand, to globally apply this logic everywhere else, we are using it as a 0 based. Now we know that, okay, 4 5 6 and so on and so forth, we know that, okay, 13 number, its most significant bit, I will go and figure out, okay, 13th number most significant bit is actually 0 1 2 and 3. So it is the most significant is actually at 3 locations. So for sure, after this, everything will be a 0, right? No, like nothing will be contributed, because it is a maximum number, and its most MSB, most significant bit is at the third location. Now coming on back to, bhaiya, what is the contribution? Again, I'm just logically showing you what's the contribution of that third bit. At third bit, you will see that you will have the sum as this, which means at the third bit, bit sum, in the bit sum array, at the third bit, you will have a 1 2 3 4 5 and 6. So in the bit sum array, at the third bit, you should add a 6. But bhaiya, how to find this? Now we will see a trick for that. Okay, for the most significant bit, I can easily say that, okay, this is the one right here for sure. Now if I ask you, what is the first number? What is the first number where you will actually have a 1 at the third bit? What is the first number where you will have a 1 at the third bit? So you might just go in a multiple of 2. You will see this is the first number having 1 at the 0th bit. This is the first number having 1 at the second bit. This is the first number having 1 at the, this is the one having the, this is the first number having 1 at the first bit. This is the first number having 1 at the second bit. This is the first number having 1 at the third bit. This is how in a multiple of 2 we keep on going. So we know one thing for sure, that the first number having 1 at the third bit is actually a 8. And currently I am at number 13. So for sure, I know every number from 8 to 13 will actually be having my third bit as set. So I will just simply go and say that answer will be 13 minus the first number having my third bit as set is actually 8 plus 1. So as to say, because 13 minus 8 plus 1 is actually same as 6. 1 2 3 4 5 6. 6 value I should add in my answer, and that's how I will get a 6. But bhaiya, how will we figure out the first number having third bit as set? Simply, you know that you will have to go and check, okay, for number 13, what is the MSB, most significant bit? That is what you want to check for. So first you have to figure out that which bit I am going and looking for. I'm looking for the third bit, which means my number 13th most significant bit is the third bit. So I'll just simply can do a log 2, like log, when I say log 2, I mean log 13 to the base 2. So I'll just do a log of 13, which will give me a 3, because 2 raised to the power 3 is actually a 8. So for sure, it is just saying that what power of 2 raised to the power some power of 2 should actually be equal to 13. Now it will be actually in some decimal values, but we want the we just want a whole number. So we'll just get a 3, which will say me 8. Which is less than equal to 13. So this will actually go and say me that third bit is the MSB for this number 13. So I know that the bit is third. So now I can simply go and say bit is third. Bro, 2 raised to the power 3 will actually give me 8, which will say third bit. And for sure, I just want to know third bit first number. So 2 raised to the power 3 will be the first number. So it is a 8. If I say my bit is 2, my second bit should actually be a 1. So what's the first number? 2 to the power 2, actually a 4. So this is a first number having my second bit as 1. Now coming on back, so now we have got to know that okay, for this value, which means for the third bit, I have found the answer, which is n. Again, that is, this value is a n. Let's name this value as a cn. How will you find this value cn? By simply first going and finding the MSB of your number n, which is log 2 to the number n, then going and finding the value itself, which is, let's name it as a MSB. Now you will say 2 to the power MSB. This will give you a value which is this 8. Let's name it as a cn. New value, let's say cn, current n number. So this is the n minus cn plus 1 will give you MSB count. Okay, now I've got the count of this MSB. But bhaiya, will you apply the same formula for all the bits? No, I cannot. Because for sure you can see that okay, other bits are not a 1. How will you go about applying the formulas? Okay, you have got the answer for your MSB. N as 13, you have got the answer for your MSB. But you cannot directly go and jump. Bhaiya, okay, I know that okay, my up till 8 is done. So what I can do right now is I can simply go and jump to number 7 and then I can start from number there itself. No, because you missed these values, you missed these values, you missed these values, you missed these values. These also should be added. Like what about these values corresponding to this range from 13 to 8? You added once, that's great, but you missed these values now. So what about these? Let's go and add these values. How will we see this? We will see. Okay, now for this number 13, if I go and say I want some uniform logic or trick, so that I should be able to find out the number of set bits. So here, while looking at the problem itself, I figured out that okay, bhaiya, right now for this all we added. Now for this we have the answer. And we also for sure know that above this, everything will be 0. Because this was the last bit. 8 was the last bit having my 1. So for sure, above everything for that will be a 0. For the third bit. Okay, that is one thing for sure, that anything above I can include and the third bit will never change. And I have also got the answer for my third bit. But what about the remaining bits? Now let's come on to my remaining bits. Here you will see, firstly I'll show you what is from the view, from the visual, how it will look like, and then we will go on to the intuition behind it, that how we actually derive it. So we will see that okay, we were at number 13. If we go back the 8 bits, then we will find out that okay, we have 1 2 3 4 ones at this location. Okay, 4 ones at my first bit and 4 ones at my 0th bit. Oh, that's a 4 ones here, 4 ones here, 4 ones here in my last 8 numbers. From number 13 to the last 8 numbers, I have my uniform count of ones. And if we just go and look at the similarity, it is nothing but if I am looking for the last 8 numbers, it is 8 by 2, which is 4. And bhaiya, okay, you took for 13, but what about my range is something else? Again, okay, let's say your n was 11. You, let's say, took the last 8 numbers. Still, you will see, okay, 1 2 3 4 count here, 1 2 3 4 count here, 1 2 3 4 count here. Again, it is nothing but last 8 bits are having, last 8 numbers are having, for every of those bit locations, my count is nothing but last 8, which means 8 by 2, it's a 4. That is a good thing, but bhaiya, how, like why? Big question is why. So the first basic intuition in this is that okay, third bit you can either have a 1 or a 0, right? So third bit is for sure fixed. If the third bit is for sure fixed, for other bits I have what options? Either I can place a 0 or a 1, 0 or a 1, 0 or a 1. So I know it has 2 options. It has 2 options. In total, I have 8 options. Now again, what could have happened that okay, at the third bit I could have placed my 0. So again, for the bit number 2, bit number 1, bit number 0, I have 2 options, which means in total I have 8 options. Now for sure, if I have 8 options, which means I'm placing either a 0 or a 1, and they are for sure 8 options. So I can half times I'll place a 0, half times I'll place a 1. That is the reason 8 by 2 is actually a 4. That is the reason I will have half in the last 8 iterations. Half times I will have a 1, half times I will have a 1, half times I will have a 0. Half times I'll have a 1, half times I'll have a 0. But bhaiya, one issue. Here you told us that okay, 1 was there, which means if I go and place, so I'm just saying that okay, all these are ones, then okay, then it is for sure true that okay, I am placing half of times my 1 and half of times my 0. But in other cases, when it is only a 0, which means when it is only a 0, then again I am placing half times as 1 and half times as 0. But what about it's a mixture? Because in this problem you showed us a mixture of ones and zeros, because you can either have a 1 or you can either have a 0. So you showed us a mixture of ones and zeros. Now in that you will see that when we form the binary numbers, we form in the form of a symmetry. They come in the specific order, in the specific symmetry itself. Thus even if we mix them, which means even if ones and zeros come like this, still they will actually follow the pattern of having equal number of ones and zeros in the order of, let's say, 8. So I would know that okay, I can go on to last 8 numbers and I will find equal numbers of ones and zeros. So now ultimately we have figured out that I was at number 13. I got my I got my number of count of set bits for my MSP. That was nothing but n minus cn plus 1. N was number 13, cn was number 8. How I figured that out? I just simply went on and said log of number 13 to the base 2. I got the number as a 3. I found my 2 to the power 3. That was my number 8, and then I got this plus 1 so as to get the entire range, and I will have a 6 bits. And for this range from 13 to 6, because 13 minus 8 is actually nothing but 5. So 13 minus 8 is 5. So from the range from 6 to 13, I know that for all the remaining places, my value will be nothing but cn by 2. Cn is this, cn by 2. So it is a 8 by 2, 4, 8 by 2, 4, 8 by 2, 4. So for sure I will know, okay, 4 bits are in this range. 4 bits are in this range. But bhaiya, that is okay. Numbers are done up till 6 and 13. But our ultimate aim, maqsad, was from 1 to 13. That was our maqsad. Again, so I just simply go on and say, now I will start off my n from 5 itself, which simply means okay, my new n is nothing but n minus cn. So my n is 5. Okay, now I'll start my n from 5 itself. But remember, whatsoever you will find the answer for this specific n, you should add in your bit sum. Please don't replace it, add it, because you want the sum of all these set bits. Okay, so what I'll simply do is I'll find the sum of set bits in this range. That's great. Again, the same exact formula which we can apply. We know it's an n, we will find its MSP. MSP is actually a 1. So we will have to firstly check the contribution of the MSP itself. I'll simply go in MSP. I know that's a location 2, which is the second bit. I'll find my Cn, which is 1 left shift MSP, or I can also add it as 2 to the power MSP. Both are same thing. It will give me a 4. I know that up till 4 is the first location having second bit as set. So I'll know that okay, only 2 things, only 2 numbers, which means 5 minus, which means n minus cn plus 1 are the number of numbers impacting my MSP. So I'll just simply add my n minus cn plus 1, which means I'll add only 2 values in my MSP. So I'll add a 2. So again, it was a 6, you saw it was a 6 here, it was a 4. I'll simply add a 2 at this location. I am adding a 2. Okay, great, I'll add a 2 here. Then bhaiya, what about the remaining values? Again, in the same way, I know that okay, I can check for the last 4 bits, because again MSB is a 2, so my cn actually a 4. So I can check for last 4 bits, and 4 bits will have equal number of ones and zeros. So I'll check for last 4 bits. Last 4 bits will have equal number of ones and zeros for the remaining portion. So it will be a cn by 2, cn by 2. You will see 2 bits and 2 bits are set in the remaining portion. So I'll just simply add a 2 for those remaining portions. So here I'll add a 2. Again, adding a 2 at these bit locations. So I'll add a 2 here, add a 2 here. Now again, n will become a n minus cn. So now my n will become a 1. Now 1 and 2 are the base cases. So what I'll do is I'll have a base case. Okay, if n is 1, then for a bit 0, simply add a 1. If n is 2, then you know that, okay, if n is 2, which means you have a number 1 and 2. So for 1, you will add a bit 0 as 1, bit 0 as 1. For number 2, bit 1 as 1. You will add it. Okay, that is the base case which we can handle out. And that is how, for the range of 1 to n, in this log n operation, in this log n to the base 2 operation, I will be able to find this bit sum array, this entire bit sum array. So for this range of 1 to n, in log n time, I will be able to find this bit sum array. And this is the entire thing which you have to remember. This entire proof you have to remember of entire thing. And again, the trick is, if you are given a range of 1 to n, you want to find the bit sum, which means what all bits are set, and you want to find the sum of that. So remember, and again, you can also bifurcate that to a sub problem. Let's say if you are asked to find in the range, if I go and ask you to find it in the range, then again you can apply the same formula. So in log n time, you will be able to figure out the bit sum, which means corresponding to every bit, like 0th bit, 1st, 2nd, 3rd, 4th, and 5th. Every bit corresponding to every bit. What is the bit sum so far? Bit sum, which means number of set bits at this location from range 1 to n. This is the entire trick which I want to tell you. Now, when this entire thing is done, my answers ultimately done, because I will be able to figure out, if I go back, where was this? Yeah. Now my ultimate aim was, this was taking a k time. I can reduce this to a log k time. And that's how I can simply solve it in log k square. Log square k. So let's have a quick look at the code. It's pretty simple, but the main thing was the trick itself, which I showed you. So as I showed you that I'll have my L and R, because I'll just do a simple binary search on my L and R. I can have it as a 1 also, no worries, because it will never go as 0. So I'll do a binary search on my L and R, because you remembered my nums can go up till k, 1 to k. Now, and that's a worst case. Again, it will be less than k, but I'm just saying, well, let's take the worst case possible. So for sure, that is the case, nothing but my k value is nothing but a simply 115. So I just took it as a 115. Now final answer is the largest possible value of my nums. So I'll just simply do a binary search on this range. Now simple binary search trick, binary search template. If L is less than or equal to R, then you will go and check, which means you will go and check for some values. Then if answer is less than or equal to k, then simply increase your L by mid plus 1, else decrease your R by mid minus 1, and keep on updating your answer with the current mid value. Now this mid is the nums value, which I am actually satisfied with. So now this is concept which you are clear with. Coming on back, I will find the mid. Now I'll simply say, currently I will go and have to find my bit sum. So I just made my bit sum empty, because for this range right now, because you remember, right, in bit sum you are keep on adding. So it's good to actually empty the bit sum in the beginning, because for this mid, my task right now is from 1 to mid, I will go and have to find the bit sum array, because that will actually help me to add up and compute the power value for me. So in 1 to mid, I have to find this bit sum array for this. So okay, this is a new mid. So again, bit sum array should be new itself. So I just made my bit sum array as empty. Now when this portion is done, I will go and solve my mid. Now this solve mid just will populate my bit sum array with the corresponding set bit count from 1 to mid range. Right? Okay, great. Now but you remembered that having a bit as set was just a one part of the problem. The other part was that I mod x should be actually equal to a 0. So if the bit is set, that's great, but it should also be divisible by x. So I'll do the same thing when I have, again, I'll show you the solve code again, but when let's imagine that as a black box. When this entire thing is solved, I'll go and ask, okay, what is the answer? Again, you remembered my k is 115, right? Which means my num, or basically my mid value, can go up till 115. Right, worst to worst case. I'm saying, okay, very, very, very worst case. Now, for sure, 115 is nothing but a 2 raised to the power 15. like a 2 raised to the power 53 is nearly more than 1e15. So I took this value again. I didn't remember that. I just put in my computer some random values. I tried for 40, I tried for 50, I tried for 55, and then I thought, okay, this is the nearest value to 1e15, which is more than 1e15, and thus I took this 53 as a value. So I will know that, okay, I will have 53 bits, right? I'll have 53 bits. So I'll go on to all of my bits, and my bit sum is containing the count of a set bits at the ith location. But remember, this ith location is 0 based, but my divisibility I mod x needs to be 1 based. So I'll simply add a +1 to actually just make my divisibility satisfied, and I plus 1 mod x, if it actually equal to 0, then I can simply add my bit sum in my answer. Okay, that's great. Now that is simply nothing but my power value. So simply the power value, if it is less than equal to k, then I can try for a larger power value, right? So I can try for larger mid, and else I'll just try for lower. So I can update my answer, and that is the answer I'll return. Now coming on to the solve function. Solve function is exactly same as the above one. Simply a 3 base cases. If n is 0, simply return. If n is 1, simply add in the 0th bit 1. If n is 2, then you know that you have two values, 1 and 2. So for 1, add the 0th bit as 1. For the 2, add the 1th bit as 1. Now comes the interesting part, which I already showed you. If the number was 13, you will go and find the MSB. MSB is a number 3, which is log 2 of that, like log 13 to the base 2. You will find the MSB, which is the 3. Now you will have to find a number Cn. Okay, what is the first number? What is the first number having the third bit as set? So that will be nothing but one left shift MSB times, which is nothing but saying 2 raised power MSB, which is saying 2 raised power 3. Okay, I have got my number Cn. So n is this, Cn I have got 8. So you remembered, firstly, for the MSB, I will add the contribution as n minus Cn plus 1, which is nothing but 13 minus 8 plus 1, which was a 6, the contribution of MSB. Now when this MSB is done, what about the other remaining values, right? Other remaining values after the MSB. So for that, I'll go on from 0 to less than MSB, and then for every of those bits, I'll add a Cn by 2. Now when this portion is done, again, up till so far, I have computed for the range of like 13 to 6. From 5 up till 1, it is still remaining. So just shift your n to a 5. So your n will become a n minus Cn, right? N will become a n minus Cn. So your n will actually become a n minus Cn. And then again, go and solve until you'll reach simply a base case, right? And that's how you can simply compute your bit sum array. And again, as I told you, when the bit sum array is computed, you will simply get the answer. Again, the time complexity is actually 53, because you will see it's 53 times you are going on, which is nothing but log k, right, to the base 2. And for sure, for every of those to find the bit sum, you just need a log k operation. As we saw previously, it's a log square k, and the space is O of 1, because it's a constant space, 53 space, that's okay. So that is, we have got to know from this answer. And this is nothing but just saying, okay, sum is, because we are adding something, so for sure it is more than equal to k. So for me, nums will always be less than my k itself, num value. Cool, that's pretty much it. It has been a bit, like, it has taken 42 minutes, but I hope that you guys got it, because I want to explain the trick, because it's very, very, very useful, and this is going to be helpful for you in the many problems. That's a bit manipulation trick which is very useful. Cool. Bye bye. Thank you so much for watching. See you guys in the next video. Until then, goodbye, take care, bye bye.